Hi, welcome once again. Thanks for joining me today. Really glad that you're here. Today we're going to talk about solving systems of equations with three variables. And of course, remember we have been talking about solving systems of equations with two variables. And when we do that, we need two equations to do that. So now when we have three variables, we're going to need three equations in order to be able to do that. If we expanded that out, let's say we wanted to solve a system with four variables, we would need four equations to do that. So however many variables you need or have, that's how many equations you need in order to solve for all of the variables. So let's take a look here. First of all, the possible number of solutions. Well, just like before, we could have a system with no solutions. Uh, and one example might be something like this. Now, if we have an equation with three variables, that equation represents a plane. So remember, a plane is just a flat surface. So if we have three different planes that happen to be crossing at different places, we aren't going to have any single solution to those. And you might remember that when two planes cross, they cross in a line. So the intersection of these two planes is this line right here. The intersection of these two planes would be this line right here. Okay, so notice they don't have any points in common on all three of these. So we have no solution in this case. If we had three parallel planes also, that would give us no solution as well. Okay, we could have one with one solution, and we'll look at that in a second. And we could have infinite solutions. So I have one here with infinite solutions. Notice all three planes happen to cross at one place. And so this line here, where those three planes cross, is our solution set. There's going to be an infinite number of those points along that line. So infinite solutions. And we could have a single solution. So let's say we have something like this, where we have this plane here, we have this plane here, and then this one kind of cutting across. And so you might notice here, if we kind of turn this one, this point right inside here is the intersection of those three planes. And so in this particular case, we would have one solution to our system of equations. Okay, so hopefully that gives you a good visual idea of how this works. Again, I mentioned to solve a system with three variables, we have to have three equations to do that. So our first example is just how can we check our answer? So we're going to verify that this point is the solution to the system of equations. So if we're given a question like this, remember just like before when we had to verify, we had to check the point in all of our equations. So we're going to do that here. We're going to take the point 2, 1, negative 3. Now remember on our xy plane, we would just have 2 points. So this is called an xyz plane. We have a third dimension here. Um, and so we have 3 points. This represents a point in space instead of just on a coordinate plane. Okay, so we have our equation 4x plus 2y plus 3z equals 1. And we're going to verify that this will actually work in there. So I have written our equation here, and I substituted in 2, 1, and negative 3 for the three different variables. So we end up with 4 times 2 plus 2 times 1 plus 3 times negative 3. And is that equal to 1? And I put a little question mark there because we don't know yet if that's actually true or not. So simplifying, we get 8 plus 2 plus negative 9 equals 1. Well, 8 plus 2 is 10, plus a negative 9, or 10 minus 9, does indeed equal 1. So that checks out. Okay, we can do that same thing for our next equation. So 2x minus 3y plus 5z equals negative 14. We're going to do the same thing. Plug each value in. So 2 times 2 minus 3 times 1 plus 5 times negative 3. And is that equal to negative 14? So 2 times 2 is 4, minus 3 plus a negative 15. Is that equal to negative 14? Well, 4 minus 3 is 1. 1 minus 15 is negative 14. So it works for that one as well. And then the last one here, We have 6x minus y plus 4z equals -1. So go ahead and substitute 2, 1, -3 in. We get 12 minus 1 plus a -12. And is that equal to -1? Well, 12 minus 1 is 11. Minus 12 is indeed -1. So it does check out. So this is the solution to this system of equations. Okay, so now we're going to move on. We're actually going to solve a system on our own here. So example 2, solve the system using elimination. So remember, with the elimination method, we had a set of steps that we used to do that. I didn't list out the steps for this because you kind of already have an idea of how those steps work. But I did make a couple of notes here. So the first thing we're going to do is eliminate one variable by using one of the equations twice. Okay, so I'm going to use equation 1 and 2, and I'm going to eliminate the y's. So notice for 1 and 2, we have 1y and -2y. So I have to get this top one here so that the y is -2, or, well, just 2. So let's multiply through that equation by 2, which I have shown right here. So 2 times 3x plus y minus 2z equals 10. When we distribute that 2 on through, we get 6x plus 2y minus 4z equals 20. And I bring down equation 2 right here. So 6x plus 2y plus z equals -2. Okay? And remember, since these are opposites of each other, we're going to go ahead and add the two equations together. So 6x plus 6x is 12x. 2y minus 2y is 0, so that it is eliminated. -4z plus z is -3z. And 20 minus 2 is 18. Okay? And now I'm going to use equations 2 and 3. So notice I use this equation 2 twice. Once with equation 1, once with equation 3. We're going to do the same thing and eliminate the y again. So this time, since we have this one is bigger, it's 4, so I need to multiply equation 2 by 2. So I rewrote equation 2, and I'm multiplying it by 2. So distributing on through, 2 times 6x is 12x, 2 times -2y is -4y, and 2 times z is 2z, and that is equal to 2 times -2, which is -4. Okay, so here is this equation multiplied by 2, and then I just brought down equation 3. So x plus 4y plus 3z equals 7, right below it. Okay, again, they are opposite, so let's go ahead and add the two equations once again. So 12x plus x is 13x, -4y plus 4y is 0, and 2z plus 3z is 5z. -4 plus 3 gives us, or sorry, -4 plus 7 gives us 3. Okay, so from there, I just rewrote those two equations on top of each other. So this might look a little more familiar. We have two equations with two variables, which you have already done before. So now it's kind of like a problem that we have done earlier on. So we could multiply this one by 13 and this one by 12 if we wanted, but the numbers are going to get a little big. So let's multiply this one by 5 and this one by 3 so that they both end up being 15, and we can eliminate the z variable this time. Okay, so when we multiply through by 5, 5 times 12 is 60x, and 5 times -3z is -15z. 5 times 18 is 90. And for the bottom equation, 3 times 13x is 39x, and 3 times 5 is 15z. 3 times 3 gives us the 9. Okay, so once again, they are opposites of each other, so we're going to add again. So 60x plus 39x is 99x. -15z plus 15z is 0. 90 plus 9 is 99. So we have 99x equals 99. Hopefully that's pretty easy to see what it is. Divide both sides by 99, and we get x equals 1. Okay, so we finally have one of our answers so far. X is 1. So now we can kind of work backwards from there. So take the 1 and substitute it into one of our equations. So I just decided to choose this equation right here, and I'm going to substitute the 1 back in. So 13x plus 5z equals 3. Putting in 1 for x, we get 13 plus 5z equals 3. So subtract 13 from both sides. 5z equals negative 10. Divide both sides by 5, we get z equals negative 2. Okay, so now we have 2 of the 3 variable answers that we're looking for. We just need to find the third one. So to do that, go back to one of our original equations now. So again, see how we're just working backwards here? So I'm going to choose this top equation, and I'm going to substitute 1 in for x and negative 2 in for z, and we can solve for y. And notice kind of the reason I chose that one is because it's 1y, less chance for error in algebra there. So I chose that one on purpose because y is all by itself already. So when we put in 1 for x, we get 3 times 1 is 3, plus y, minus 2 times negative 2. Well, minus 2 times negative 2 is plus 4. So 3 plus 4 gives us 7. So we have y plus 7 equals 10. Subtracting 7 from both sides, we get y equals 3. Okay, kind of a long process. And it is a process, definitely. Just something we kind of have to get used to. So of course, whenever we get our answer, we do want to double check our answer is correct. So choose a different equation than the one we just used. So I'm going to choose the bottom one to check my answer. And if we put in x, y, and z, we should end up being correct. It's really not necessary to check it in all 3. The odds of finding a set of 3 values that work in one but not one of the others is probably pretty small if you've done all your work correctly. So you just need to check it in one of the 3 equations. Okay, so if we put in 1 for x and 3 for y and negative 2 for z, we get 1 plus 4 times 3 plus 3 times negative 2. And is that equal to 7? Well, 1 plus 12 is 13 minus 6. 13 minus 6 is 7. So it does check out. So our answer is the point 1, 3, negative 2. Okay, next example here. This time we're going to solve using substitution. So remember, we've had 2 methods in the past, actually 3. We had graphing, solving by substitution, and solving by elimination. These are kind of hard to graph, obviously being 3 variables. We would have to graph planes and it would be kind of difficult. We haven't done that really before. So we're not going to use graphing, but we do have the algebraic methods, elimination. And so now we're going to use substitution. So when we're using substitution, solve one equation for one of the variables. So choose an equation, it doesn't matter which one, choose one of the 3 equations and solve for one of the variables. So I noticed that z is kind of plus z here. Looks like an easy one to solve for z. So I just brought the equation over here and solved for z. So add x and subtract 5y from both sides. We get z equals x minus 5y plus 8. Okay, so far so good. So now what we're going to do is substitute that back into both of the remaining equations. So when I put it into the top equation, we have x plus y minus z. And remember, this is what we just found that z is. So I just took this, substituted it in there for z, and now we can kind of simplify this down. So remember, it's very important to put parentheses around there, especially when there's a negative sign. Because if you don't put parentheses, you'll forget that we have to distribute this negative sign on through, and it'll mess up your answer. So be careful with that. But if we distribute the negative on through, we get negative x plus 5y minus 8. So we have x plus y minus x plus 5y minus 8 equals 4. So we have 6y minus 8 equals 4. Adding 8 to both sides, we get 6y equals 12. Divide both sides by 6, we get y equals 2. Now in this particular case, it's kind of nice because notice here the x's ended up canceling out. That's not always going to happen when you're solving some of these, so just be aware of that. But in this particular one, it worked out really nicely, and the x also canceled out for us. Okay, so even though we did find what y is, let's go ahead and solve the other one, or find out what the other one is when we substitute in z. So that is this equation here, the middle one. So 3x plus 2y plus 4 times z. And remember, this is what z was right here. So 4x, and then, so if we distribute 4x minus 20y plus 32. So combining like terms, 3x plus 4x is 7x. 2y minus 20y is 18y plus 32 equals 17. So now subtract 32 from both sides, and we get 7x minus 18y equals negative 15. Okay, so far so good. If we had not eliminated x here, we would now have two equations in two variables, and we can continue with our substitution from there. But we don't have to do that because this came out and we were able to solve for y a little easier. So let's take y, which is 2, and plug it in right here. So 7x minus 18 times 2 equals negative 15. Negative 18 times 2 is negative 36. So 7x minus 36 equals negative 15. Adding 36 to both sides, we get 7x equals 21. So divide both sides by 7, we get x equals 3. So notice again, we're just kind of working backwards here. Once we find one of the solutions, we work backwards until we find the other two. Okay, so we now know what x is, we know what y is. So choose one of your equations. The one that looks easiest to work with from our original equations is the top one. So x plus y minus z equals 4. Put x and y back in, which was 3 and 2. So 3 plus 2 minus z equals 4. 3 plus 2 is 5, so 5 minus z equals 4. Subtracting 5 from both sides, we get negative z equals negative 1. Of course, if we divide both sides by negative 1, we get z equals positive 1. So we now have 3, 2, 1 is our solution. So let's choose one of the other equations now and double check our answer. So let's check this middle one. If we put in 3 for x, 2 for y, and 1 for z, 3 times 3 is 9, 2 times 2 is 4, 4 times 1 is 4. And is that equal to 17? Well, 9 plus 4 is 13, plus 4 is indeed 17. So it does check out. So our answer is 3, 2, 1. And remember, this is just a point in space. So all three of our planes here intersect at this one point in space. Okay, a couple more to take a look at here. So example 4, solve each system. So we have a system here, x plus y plus z equals 3, 4x plus 4y plus 4z equals 7, and 3x minus y plus 2z equals 5. Okay, so looking at that, you might notice something interesting here. If we take and multiply this one by 4, you might kind of notice what's going to happen here. So multiplying this top equation by 4, so that, say we want to try to eliminate the x's, okay? So we multiply that one by 4. So we get 4x plus 4y plus 4z equals 12. And if we bring down this middle equation and subtract the two, notice what happens. 4x minus 4x is 0. 4y minus 4y is 0. 4z minus 4z is 0. So we get, oh, and 12 minus 7 is 5. So we get 0 equals 5. Well, that's a false equation. That's not really true. We know that that's not true. So this is a case where we have no solution. These are actually parallel planes because they wouldn't cross. So since those two planes are parallel, there cannot be a solution. Okay, and in our final example, example 4b, we have these three equations here: x plus y plus z equals 4, x plus y minus z equals 4, and 3x plus 3y plus z equals 12. Okay, So remember, I'm just going to go ahead and use elimination. And it's kind of nice. I can use this one since this is minus 1z and these are both plus 1z. I can use this equation, the middle one, to eliminate z from both of them. So x plus y plus z equals 4 and x plus y minus z equals 4. If we add those two, we get x plus x, 2x, y plus y, which is 2y. Z minus z is 0, so it cancels. And 4 plus 4 is 8. So the z is eliminated. Okay? If we do that same thing here to the second and third equation, when we add those two, x plus 3x gives us 4x, y plus 3y gives us 4y, negative z plus z is 0, and 4 plus 12 is 16. Okay, so I rewrote both of those equations on top of each other. So now we have a system of two equations with two variables, which you know how to solve already. So if let's say we want to try to eliminate the x's now. Okay, so in order to do that, we need these to be the same, so multiply the top one by 2. So when we do, 2 times 2 is 4. So we have 4x plus 4y, and 2 times 8 is 16. So 4x plus 4y equals 16. Well, that happens to be the exact same thing that this was. So when we subtract the two, we get 0 equals 0. And you might remember from before that when we have something true like this, like 0 equals 0, all the variables have canceled out. So in this particular case, we have infinite solutions. Okay? For now, I'm just going to have you say infinite solutions. Um, just know that the solution is the set of all ordered triples x, negative x plus 4, and 0. So this is the true answer, but for now, I'm just going to have you say infinite solutions. We're not going to worry about finding all of the ordered triples at this point. Okay? Um, so 3 equations, 3 variables, and all of the possibilities. If we have one answer, if we have no solution, or infinite solutions. So I hope that will help you out when you go to work out these problems. And that's all I have for you today. I hope to see you again soon. Thanks.